numbers not equaling each other, you'll see that the equation won't work out, and thus this interval will not have a spot in space where the electric field equals 0. Okay? But I'm just kind of doing this preemptiveness to simplify my math, because we have a certain amount of time on the test to work on, right? Okay, so instead of having to do my math 3 times, I only have to do it once now, because of my strong conceptual understanding. Our strong conceptual understanding for physics, right? So what are we going to do here to figure out what spot holds an electric field equal to 0? Well, we'll look at our vectors, right? We know that the E net will equal the electric field caused by the first charge plus by the electric field by the second charge must equal 0, correct? Okay. We can take out these vector signs by noticing the direction for each of these. So the direction of the direction of Q2 will be to the left, right? And then the direction for Q1 will be to the right. So here's E2, here's E1. Thus we can say E1 minus E2 is equal to 0. Or E1 equals E2, right? So if E1 equals E2, and we break these up into kind of what I wrote over here, we have KQ1 over R1 squared is equal to KQ2 over R2 squared. But let me ask you this. What is our R1 and what is our R2? They're not the same, right? Yes?
Would R1 be X and R2 be D plus X?
Awesome. So if we, kind of just reconfigure, this is where E net equals 0. This is where Q1 is. And this is Q2 is. We know this is D. And if we define this to be, X, we can use whatever variable we want. But just so we can conduct some algebra here, we'll call this X. The distance from Q1 to that point will be X. The distance from Q2 to that point will be X plus D. Thus R1 equals X, R2 equals X plus D. Is everyone following along? Questions? Not too bad, right? Not too bad. But let's plug it in and see what we get. So we'll have k's on both sides, so we can actually cancel that out, right? We'll plug it in, so we have Q1 over X squared is equal to Q2 over X plus D squared. Now, all we got to do is solve for X and we have our answer, okay? But let's simplify this out and see what happens, okay? So if we factor that out, we'll have X squared plus 2XD plus D squared, okay? So we have Q1. I'm just going to kind of erase that because I simplified it here, or factored out, not factored, foiled. Yeah, foiled. Yeah, so let's try timesing over each side, get everything in the numerator. So then we have Q1 times X squared plus 2XD plus D squared is equal to X squared times Q squared. Okay. What do we see here? We see a polynomial. Okay. What do we do if we want to solve for not just the polynomial? We have a binomial, right? What do we do for those? How do we solve for a variable in a binomial? Quadratic equation, right? So to do our quadratic equation, we We have to solve for 0, find what our A, B, and C is, and then get our answer, okay? So let's get this to 0 so we can kind of get x there, maybe divide the q1 here, okay? And then we'll subtract that over. So we'll have x squared minus x squared q2 over q1 plus 2xd plus d squared equals 0, okay? I'm going to kind of bring this up here. Thus, we have, factoring out the x here, we'll have x squared times 1 minus q2 over q1 plus 2xd plus d squared equals 0. And now we have our A, our B, and our C, okay? And if we remember our quadratic equation, it's negative b plus or minus the square root of b squared minus 4ac all over 2a. Then we can solve, okay? So, you know, if you're doing variables, you can kind of just have this as your final answer, just essentially plugging in what b and ac would be. Thus, we can look at this and say b is negative 2d, right? Yeah, sorry. So 2d plus or minus the square root of 2d squared minus 4a, which is 1 minus q squared over q1. I mean, not q squared, q2. Okay, sorry. Q2 times c, which is essentially d squared, all over 2a, which is 1 minus q2 over q1. Now plugging in our variables, okay, we see that our d is equal to 1, our q2 is equal to 6 microcoulombs, and our q1 is equal to negative 2.5 microcoulombs. We don't need to, you know, this is just kind of SI pro tip kind of thing here, shortcut. You don't need to do the times 10 to the negative 6 for our micros, you know, convert it to SI, because every time we have a q here, they're divided by each other. Thus, our micros will cancel, right? So just to save, you know, calculation time, you can see that and simplify your writing. So we have negative 2 times 1, okay, plus or minus the square root of 2 times 1 squared, so it's just 2 squared, minus 4, 1 minus q2, which is 6 microcoulombs over q1, which is negative 2.5 microcoulombs. But I'm going to keep that negative out. Okay, why am I going to do that? We already accounted for direction. So that negative there is just to show that our electric fields are going here. But as soon as I made this and plugged in a negative right here, I've already taken that negative into account. If I were to do it again, it would be as if we were adding our two electric fields, and it would be inside, and we wouldn't get, you know, like a good number, okay? So we take the absolute values of our charges. And if you look in the book, actually, we'll see that, you know, electric field is equal to the absolute value of Q, and it asks you to take into account direction with the charge. So you might see in your formula sheets the absolute value of Q. Okay? Thus, we have our 2.5 times d squared, which is just 1. Awesome. And then 2 times 1 minus 6 over 2.5. Okay? If we're going to solve this out, we get two answers, of course, the way quadratic formulas do. We'll get x equals Here we go. We get x equals 1.82 or x equals negative 0.3922. Which one do we use? Which one do we use?
Smaller.
The smaller one, the negative 0.3922? Why?
Because it feels like the d would be much larger than the distance of x, wouldn't it?
No, excuse me?
Wouldn't d be a lot larger than x?
So d should be a lot larger than x? We don't know that. It should be to the left. So we know it should be to the left. But we already accounted for that, okay? So looking back up here, when we defined x, it was, some positive number to the left, okay? If we were to say, this is y equals 0, x equals 0 here, and we plugged in negative x right here, and thus instead we had x minus d. In this one, then we'd use our negative number, but since we already accounted for it being some distance to the left, it's going to be our positive number, okay? Because if we were to use our negative number, that'd be like saying some distance in between the two, okay? Which is not true. So it's going to be x equals 1.82 meters to the left. Okay, because we defined our radial distance to the left of Q1, some positive x to the left of Q1. If we were to plug in negative x over here, then we'd use our negative number that pops up. And you could do this the same way, like instead of here, we'd have negative 2xd, right? If it was x minus d squared. And if we were to have x squared minus 2xd, we can see that here we would have a negative number for our 2d for this one, which would cancel out that positive, thus giving us these same numbers, just negative 1.82 or positive 0.3922. Okay, so you got to be careful with these long calculations. Be wary where you've taken into account negative signs and directions and things of the such. Okay. Any questions? Yes.
Okay, so before when you expanded x plus d,
Mm-hmm.
could you just solve for it x plus d squared and then taking the square root? And that would have made it like.
I don't know. Let's try it. So we have Q1 over x squared equals Q2 over x plus d squared. So you're talking from this position?
Yeah, and then cross multiplying.
So cross multiplying, so then we'll have Q1 times x plus d squared equals Q2 times x squared. And square root both sides, so then we have the square root of Q1 times x plus d equals the square root of Q2 times x, and then divide out that. Well, actually, yeah, let's get these both on the same side, right? So then we have d Q1 equals x, Q2 minus x Q1, d Q1 equals x square root of Q2 and then divide by, well, let's see if we get the right answer. Q2 minus, looks right. Okay, thus x is equal to 1 times the square root of Q1, which Q1 is 2.5 microcoulombs. So here we need to take into account times 10 to the negative 6. We have 6 times 10 to the negative 6. Distance is just 1. 2.5 times 10 to the negative 6. Okay. Let's plug this into our calculator here. We have the square root of 2.5 times 10 to the negative 6 divided by square root of 6 times 10 to the negative 6 minus the square root of 2.5 times 10 to the negative 6. Cool. And that's what we got earlier. Awesome. Thank you. So you got a way to bypass the quadratic formula. Any other questions? Yes. Because that was given by the problem. Yes. You can make, so I made my reference like, you know, x equals 0 at the negative charge. You can make your reference however you want. Yeah, you know, your calculations will change a little bit. You should, no matter what, come to the right answer, regardless. Anything else? No? Cool. All right. So, that's number 1. Number 2. For the configuration below, which describes a solid insulative sphere with a radius a equals 5 centimeters and a hollow conducting spherical shell with thickness of C minus B, where B equals 20 centimeters, C equals 25 centimeters. Suppose the electric field at a point 10 centimeters, okay, so 10 centimeters is greater than A, but smaller than B. So over here, let's actually call this R1. R1 equals 10 centimeters. Has some electric field measured to be, let's just write electric field, you know, at 1 is 3.6 times 10 to the 3 newtons per coulomb. And this should be shaded in. I didn't know how to color it in without messing everything up on Microsoft Word. But yeah. Where was I? Radially inward. So that electric field is going to be radially inward. It's going to be very important for us. Okay, so there's our electric field one with that magnitude. Let's just write out what A, B, and C are equal to real quick. So we have A is 5 centimeters, B is 20 centimeters, and then C is 25 centimeters. Let's see, where were we? And the electric field at a point 50 centimeters from the center, so some distance out here, right? Because C is 25. So let's call this R2, which is 50 centimeters. and we have an electric field too, which is equal to 200 newtons per coulomb. But our electric field at this point is radially outward. From this info, find A, the charge of the insulating sphere. Okay, so what is the Q of the insulating sphere? So I'm just going to put I and S for insulating. What is the net charge on the hollow conducting sphere? Okay, so the Q on, I'm just going to say hollow. And then the charge on the inner surface of the hollow conducting sphere. So I'm going to just say Q inner. And then charge on the outer surface. So we'll just call this out. Okay? And, you know, naming these things are important for your calculations, yes? Yeah, you're right. I'm sorry. Thank you. So E2 is 200. Any questions thus far? You know, just pro tip, like make sure you have your names, especially when we have a lot of variables like this, pretty distinct, okay? Because then you might be like, oh, some new thing comes in and you want to call it I2, you know, like Q sub I, but you already have a Q sub I. And then you have two Q sub I's and you're like, damn, I need to go back through all my calculations, add, you know, like something, or just, you know, just naming stuff helps, especially when given a lot of stuff like this. Okay, let me get some more paper up in here. How are we going to do this? Well, what do you guys suggest first? What do you guys suggest? Gauss's law. Good stuff. Okay, Gauss's law. Anyone disagree? Why not? All right, cool. So we have Gauss's law, which states the closed integral E dot dA equals what? Awesome. So the charge enclosed by our Gaussian surface divided by the constant epsilon naught, okay, the permittivity of free space for electric fields. How are we going to create our Gaussian surface? I discussed this at my earlier review, right? I gave you guys like a little kind of concept idea. Use symmetry. Awesome. So how are we going to use symmetry? Okay, so it's going to be an imaginary surface. He says a sphere. How big are we going to make our sphere? Where are we going to have our sphere? Big enough to enclose what we're looking for. So we're looking for the charge on, you know, part A says to look for the charge on the insulating sphere. Okay, so I want to make one larger than that. Do I want to make it like this big, all the way out here? I want to make it some R inside. But let's actually make it specifically the R1 that they gave us, because we know we have a constant electric field of this magnitude. Okay? So if we make this our Gaussian surface, we can, for the Q enclosed, which would simply be the charge on the insulative material, we can pull that out, have the integral with respect to A equal to the charge of the insulative sphere over epsilon naught. Okay? And if we were to take the integral of dA, it would just be the surface area of the sphere. And who can tell me what the surface area of the sphere is? What was it? Pi r squared? 2 pi r squared? 2 pi r is the surface area of a sphere? Talk about the surface area of the sphere. 4 pi r squared, okay? This is the surface area of a circle, okay? So we're going to see it's 4 pi r squared. And then that's it, you know? With cosine, that's your final answer. If we were to continue on with our numbers, we'd plug in 8.85 times 10 to the negative 12 for our constant. You know, I have, you know, I'm notorious for not putting in my units, but like in hard problems that are new to me, when I enter like a new problem, I always put in my units, okay? Always put in my units so I could see if the problem's working out correctly, if, you know, see if I'm getting a valid answer. But right now, like I have a lot of writing to do, not a lot of space, and I've done this problem before. We have our kind of missing the units. Plus, I'm not really sure what the units for epsilon naught is. Our electric field, which is E1, right, given by this, so it'll be 3.6 times 10 to the 3. I know the units for that, newtons per coulomb, times 4 pi times r squared. Our radius would be 10 centimeters, but putting to SI, it'll be 0.1 meters, okay, squared, which equals Q inside. If we were to simplify this, we would get 4.01 nanocoulombs. Is this answer correct? Yeah? Who else thinks it's correct? Raise your hand. Yeah? Raise your hand. Who thinks it's correct? What's our sign?
Negative.
Why is our sign negative? Or is it positive? It's pointing inward, so our sign is going to be negative, right? Just like our previous problem, how we kind of accounted for the sign originally and did our math and not need it. We did our math, but didn't account for a sign. So now looking graphically, we need to take that into account, okay? So because our electric field is pointing inwards, we know that this is going to have a net negative charge, okay? Does that make sense? Any questions?
So if you solve for the outer sphere, would you subtract the charge on the outer sphere from the charge in the inner sphere? With the total charge?
So the charge from the outer sphere, you mean this cylindrical, subtracted by this one to get our, what exactly?
You'll see in the mix when we move to R2. He's asking.
Okay. Awesome. So yeah, next we are going to find the net charge on the hollow conducting sphere. So only this one. Okay? Thus, we'll set up a Gaussian surface just like we did before. Okay, but now we have a radius of R2. Okay, and actually let me put the little sub 1 right there from our previous problem. We have the same thing, right? We'll have the closed integral of E dot dA equals Q enclosed over epsilon naught. But we'll see that our Q enclosed is different, okay? We'll see our Q enclosed, so epsilon naught, this just means, you know, different workspace. Epsilon naught times electric field times the surface area is equal to Q enclosed, but Q enclosed is now different. Q enclosed is the charge on the insulative sphere plus the charge on the hollow sphere. Okay? Thus, our Q on the hollow sphere is going to be epsilon naught times E times 4 pi R2 squared minus Q inside equals Q hollow. And if we were to plug in our variables, again, we'll have 8.85 times 10 to the negative 16, no, 12, times electric field, which is now 200. Let me just, be consistent with my variables here. So E2. Okay? So let's not forget our indices, okay? Indices is really, really helpful for long calculations. Times 4 pi times R2 squared, which is 0.5 squared, minus a negative 4.01 times 10 to the negative 9 coulombs. Okay? Which equals our hollow charge. And if we were to simplify this out, we should get positive 9.57 nanocoulombs. Okay. Any questions? Yes. We do take into account E1, and that's subtracting the charges from this one. Because the electric field, the E2, according to Gauss's law, will equal, the surface area times the charge enclosed. Equals to the charge enclosed, divided by the epsilon naught. But if we remove this enclosed charge, then we'd have a smaller electric field. Actually, we'd have a bigger electric field because this electric field is going in the opposite direction. Because instead, we'd subtract it. We wouldn't subtract anything. Here we're subtracting a negative number. Thus, yeah. Any questions? Cool. Let's take a look at part C, which says, find the charge on the inner surface of the hollow conducting sphere. Dang, that's crazy. The inner surface, how are we going to do that? Who can help me? Yes. We can put our Gaussian surface between B and C. So let's try that. So we'll have our Gaussian surface in between B and C. Why are we going to have our Gaussian surface in between B and C? Awesome. Because we're only concerned with up to here. And there's an important concept that you guys should know here. Okay? The electric field inside of a solid conductor that is placed within another electric field is 0. Okay? So the electric field inside of here is 0. So this is a concept you guys should know from your readings and stuff like that. Thus, if we take a look at our, what's it called? What is this, Gauss's law? Yeah, Gauss's law. Thus, our electric field is 0. Thus, this ends up into 0. So our net charge, if I move this over here, I can times that by both sides, and it'll just essentially go away. Anything times 0 is 0. Thus, we get 0 equals our charge enclosed. But let's break up what our charged enclosed is. Okay? Our charged enclosed from this Gaussian surface is the charge of the insulative sphere and the charge of the inner sphere of our conducting shell. Thus we'll have Q insulative plus Q in. Okay. I just multiplied it to the other side, and the other side was 0. So, yeah. And we have our answer for, so we know that Q in will equal negative Q insulative, which is equal to negative 4.01 nanocoulombs. Thus Q in. And that would be our answer for part C. Yes?
So you said the electric field on the inner surface of any insulator is 0?
The electric field inside of the material is 0. Yes? Essentially, okay, here we'll have only some charge on the outside, like we'll have some charge on the inner surface and some charge on the outer surface, and they're going to be opposite in charge. And the reason for that is because this one, which we described to be negative, right, negative 4.01, it's going to attract all the positive charges to the inner surface. And then the negative charges are going to be repelled outward. Thus, we'll have some electric field radiating. Yeah, we'll have some radiating outward and inward, and they cancel within. But the reason they cancel, even though the outer one will have larger charge than the inner one, is because the outer one has a larger surface area to cover. Does that make sense? So it'll have the same density of charge, but different total charge. Does that make sense? Okay. So now what about the outer surface? So here we have Q out equals question mark. What do we do here? This is the easiest one. Around E2? We already did that over here. So we already did that, and we came up with an enclosed charge of this right here. So so Q hollow is just going to be Q outer plus Q inner. Okay, so the entire charge on our conductive shell is just going to be the sum of the charge in the inner surface plus the charge of the outer surface. Okay, and we found those two variables. So Q out is going to equal Q hollow minus Q inner. We know Q hollow is equal to 9.75 or 9.57 nanocoulombs minus Q inner, which is 4.01 nanocoulombs. And if we subtract this out, we'll get something like 5.56 nanocoulombs. Any questions? Q inner would equal to 0 y?
Because there'd be no electric field inside.
There would be no electric field attracting those positive charges inward. So if we didn't have our insulating sphere, our inner shell would have a charge of 0 because they would all be kind of pushed outwards from each other. Does that make sense? Because, you know, the charge inside of this portion will push away the charge from this portion, leaving it on the edges. And it happens, you know, throughout the entire sphere there. Good question. Thank you. Anything else? Y'all ready for the next problem? Cool. Okay. So, next problem is calculate the work that must be done on charges brought from an infinite distance away to a spherical shell of radius r up to a total charge of q. Okay, so let's kind of draw what's going on. So we have, you know, we have the spherical shell, it's radius r. Now here's infinity away. So we're going to take a charge Okay, so we want to find work. Whoa. How do we define work? Raise your hand. Huh? Work equals force over distance? Force times distance. Awesome. Okay. We can derive an equation that involves charge and potential through this. Do you guys want to go through the derivation, or you guys just want the answer? Cool. Okay. So if our force is Coulomb's law, we'll have kq1 times q2 over r squared times distance, and we're looking at some radial distance r. Okay, we'll have 2 of those r's cancel, and then this will essentially be kq1 over r times q2. kq1 over r is just our potential. Okay, so then we have work is equal to change in potential times charge. Okay, so if we're moving over some space with electric field, thus we're changing our potential if we're moving perpendicular to that, if we're moving parallel with that electric field. Does everyone understand that? But if we take this charge and we move it here, shouldn't be no work because there's no potential, right? We have empty space, okay? There's no charge here. Essentially, if we were to take this charge and push it here, because of inertia, it shouldn't take any work. There's no change in potential. Why? So would our work equal 0? I'm going to tell you that it's no. I wouldn't put something that equals 0 on my review. Okay, continuing on. What we can think of is moving one infinitesimal charge dq to it, and then another dq, and then our second dq is going to feel the resistance of our first dq, and then our third dq will feel the resistance of the 2 dqs that are already there, and then our fourth, And then we keep doing that until we get all of our charges. So we can think of, an infinitesimal work, okay, will equal moving an infinitesimal charge dq times the change in potential that it feels. So our first dq, the change in potential is 0. We don't have to worry about it. Second dq, that's not the case. That's not the case. Okay, but let's see what this delta V is. Okay, we kind of have it right here, but just kind of to break it up more elaborately, we'll see that dq delta V is equal to K times, the charge over R, because that's going to be our final position in space, and then our initial position in space will be at infinity. So KQ over infinity. And just simplifying that, it's just KQ over R, right? Thus, we have the integral of dw equals the integral of K over R times Q dq. What are going to be our bounds? 0 to R. Does everyone agree? Taken with respect to dq, right? What was that? We'll have it from 0 to Q. You guys see that? So one charge, one little dq. Keep doing that until we reach this. Okay? And this is Q equals 125 microcoulombs. So I could pull out our constants. We'll have work is equal to K over R times the integral from 0 to Q, Q dq. That's going to equal K over R times 1/2 Q squared from 0 to Q. And then if we plug that in, we'll have K over 2R times Q squared. And then that would essentially be your final answer. Okay, but just plugging in our knowns, we'll have K, which is 9 times 10 to the 9 over 2 times our radial distance, our radius of the sphere, which is 0.1 meters, times Q squared, which is 125 times 10 to the negative 6 squared. And if we were to plug this into our calculator, we should get 702 joules. Okay. Any questions thus far?
Could you go into the concept of the infinitesimal charges?
Okay, so he asked if I could go over the concept of the infinitesimal charges again. Essentially, what's happening, the reason work isn't 0 is because moving charges to one place, okay, in free space here, we'll have some of the charges acting on each other. So, we can't just move it all at once. So we'll take a little bit of charge and move it over. And then take a little bit more charge and move it over. And then those will continuously add up, okay? And that's what the integral does. It adds up little infinitesimal pieces together. So we're adding up a bunch of infinitesimal charges, Q, to get us how much charge would actually be affecting our work, right? Because our potential is going to increase as we add charge to it, okay? So the work to move our dq will be higher every dq we add to our shell. Okay? Anything else? Cool. I know some of you guys came in late. Just to let you guys know, I have evaluations to rate how the session went, how I was doing and whatnot. If you didn't get one, please make sure to come to me and get one, and you can fill it out If you do have one next to you, you can just fill it out there and leave it at the table. I'll come pick it up at the end. Don't worry about that. Now, yeah, you know what? Let's just do that now. Here you go. You can just pass this down too. That's extra? You can just leave it on the table there. I'll grab it a little bit. But yes, you guys ready for number 4? Cool. Here we have number 4. Okay, so it says, in the figure, find first the current in each resistor, so I1, 2, and 3, and then the power delivered to each resistor. Okay, so here we will use Kirchhoff's rules to solve this problem. What are Kirchhoff's rules? Who can tell me? Raise your hand. Yes, Matthew.
You have to split the circuit, the current with I.
Okay.
But if I1, it splits I1 to the I2 plus I2.
Awesome. So 1, we'll call that the junction rule. Okay, so Kirchhoff's junction rule. And that, just restating what he said already, is if we have some current I1 and I2 entering a junction, it will leave as current I3, and that I3 will equal the sum of I1 and I2. Or more simply stated, that was a very ugly epsilon, okay. The sum of the currents at a junction will equal 0. Okay, if they're entering in the junction, then it's positive current. If it's leaving the junction, negative current. Okay, in his example, I3 was our leaving current. What else do we have? From this side. Everybody's been helping me out from over here, but what about this side over here? What is Kirchhoff's other rule? The loop rule? What does our loop rule say? Ara? Alex? The sum of our potential will equal to 0. Okay, so the sum of our potential will equal to 0 within a loop. So this is inside of a junction, at every single junction that we have, and this will be for every loop that we have. Okay, so how many loops do we have here? 3, yeah, we can have 3. We only need to use 2, for our example, because we just need to make 3 equations because we have 3 unknown variables. But essentially our 3 loops, we could have 1 inside, okay, and direction is arbitrary. It's just best to kind of go with the flow of one of the batteries, okay, because then you don't have to deal with negative currents. But essentially, we will see these, and our third one would be around all of it, okay? But we don't need it because here we can account for our I1, I2, and I3 with just these 2 loops, okay? Thus, we can start our system of equations, right? We'll have our first equation given by Kirchhoff's rule of loop 1 as, if we start from this point here, okay, whenever I'm taking, a test or working out a problem, I always like to make a mark where I'm starting so I know where to end, and I don't account for anything twice. Sometimes you hit some big loops. Of course, this one's tiny, but if we had a bigger one, it might be confusing and you might mess up. So we start here, we'll have a potential jump, and let's call this, just V1, okay? This is equal to R1, this is equal to R2, this is equal to R3, just so that I could keep it in variable notation, right? And then here's V2. Okay, so we'll have a potential jump at V1. We'll have a potential drop across R2, so we'll subtract R1 multiplied by I1. Okay, and then we continue going here. Since we're going against essentially our current here, we'll have a potential jump, okay, of R2 times I2. And we're going down the battery, so we'll subtract V2 to equal 0. Okay? Any questions here? For these problems, keeping it in variables is a hot mess. Okay? I'm going to put in the numbers and kind of simplify it there because, it turns my workspace from like 1 or 2 sheets of paper, as opposed to 5 sheets of paper. Okay? So I'm going to plug in and simplify a little bit here. So we'll see V1 is equal to 24 volts minus R1, which is 28, times I1 plus R2, which is equal to 12, times I2 minus 12 volts. And we're looking for current 1, 2, and 3 because we want to find the current in each of the resistors. Okay? Simplifying this, we have 24 minus 12, which is just 12. Thus, we have 12 minus 28 I1 plus 12 I2 equals 0. Okay? Loop 2 is going to give us, if I start here, plus a potential jump of 12 volts going around a potential drop of, let's just use V2 for now. So V2 minus R2 times I2, we continue on, minus R3 times I3 equal to 0. Everyone good here? Questions? Okay, so plugging in our known variables, we have 12 volts minus R2, which is 12 ohms times I2. Let me take out that V here because it looks like it's another variable. Minus R3. Oh, I did, yeah, okay, R2. So 16 is R3, I3 equals 0. Okay, so just putting a star over here to identify our simplified versions. So we have 3 unknown variables, 2 systems of equation. How can we get our third equation? Awesome. So, from the junction over there, we'll see that I1 plus I2 equals I3. And I wish I did this up here so then I had more math space, but that's okay. I have some paper over here. Hold on. Yeah. So I just added to my math space. Okay, so here's our system of equations, and we want to find what I1, I2, and I3 is. Okay, this is just, basic algebra, but it's kind of tricky. Anyone gonna lie? This is pretty tricky. Okay, you want to know if you could either substitute in, you can elimination, or set things equal to each other. What I like to do is usually solve for one variable and then set them equal to each other to get it in terms of one or the other. But if I were to do that, like if I were to solve for I1, like let's say if I solve for I1 here, I'd have a function of I2, and then this one would be of I2 and I3, and then I'd set them equal to each other, but I'd still have 2 variables. So for this to work out first, we'd use substitution. Okay, so substitution, we can get our second variable in terms of I1 and I2, then solve for I1, and this one, solve for I1 here, set them equal to each other, and then we have a function with respect to I2 exclusively. Okay, does everyone see that game plan? When I work these problems also, like I kind of look at them, make a game plan in my head first before writing. Yes?
So are you solving loop 2 for I2, or rather loop 2 for I3 and then loop 1 for I1?
I'm solving loop 2 for I1, but to do that first, I'm going to plug this in for I3 to get loop 2 with respect to I1. There are probably simpler ways. What would you suggest?
I would suggest just making loop 2 equal to I3,
Uh-huh.
and then substituting I3 into the equation, and then make loop 1 equal to I1.
Uh-huh.
Substitute that into the equation, and then it's all in I2.
Awesome. Which is pretty much what I was going to do. So we'll solve, for I3, or we can just plug it in and it'll be the same and you can subtract it. Here we'll have 12 minus 12I2. Huh? Yeah, okay. So here we'll plug in I2 for I3, okay? So that we can get this in terms of I1 and I2, just like this is in terms of I1 and I2.
So you're solving for I2 and then I1 plus I2 equals I3.
For this one?
Is that what you're doing?
No, this one I'm keeping it with respect to I3, but I'm going to plug it in here. So 12 minus 12 I2 minus 16 I1 plus I3 equals 0. But I'm going to solve for I1 in each of these, okay? So this one, solving for I1, will essentially be, we have 28 I1, so adding it over will equal to 12 plus 12 I2. Okay, and then you divide out the 28. So we have this in terms of I1. To get this in terms of I1, we'll add that over. So we'll have 12 minus 12 I2 equals 16 I1 plus I3.
So you put I1
Oh.
plus I3 in.
Yeah, I2.
Okay.
My apologies. Divide the 16, subtract the I2, thus we have 12 minus 12 I2 over 16 minus I2 equals I1. Okay, and if we 12 divided by 16, just to kind of simplify this further, so we have the I2s together. We'll have so we'll have 12 divided by 16, which is equal to 0.75, minus 12 divided by 16, which is also 0.75. I2 minus I2 equals I1. We simplify this further, so this is 1. So negative minus a negative is like adding the 2, so we'll have 1.75 I2 equals I1. So this is to I1, this is to I1. We could set them equal to each other and then have a function with respect to I2. Okay, so then we have 0.75 minus 1.75 I2 equals, just going to simplify this further real quick. We have 12 divided by 28, which is 0. When you get a large decimal, use like at least 5. I like to 5 or 6 prematurely in your equation. So 8, 5, 7 plus 12 divided by I, which is also the same thing, but times I2. Okay, just writing that over here, we have 0.42857 plus 0.42857 I2. Solving for I2, we add that over, subtract that. So then we have, I'm just going to do it on my calculator here. We have 0.75 minus 0.42857 to give us 0.32143. We're going to add that over, so we'll have our original 0.42857 from here, plus 1.75 to give us 2.17857 I2. Divide out that 2.17857 will give us our I2 exclusively, thus 0.32143 divided by 2.17857 is equal to 0.14754. So we found one of them, I2. And essentially what we can do is plug this into our other one, get I1, and then we plug those two into here and we get I3. Okay, so kind of coming up here to complete our work, we have I1 is equal to 12 plus 12 times I2, which is 0.1475 divided by 28. Thus I1 is equal to 0.49179, rounding up here, in amperes. Thus I3 is going to equal the sum of the two. Okay, so I3 is going to equal this plus 0.14754. So we have this one saved already in our calculator. We'll plus 0.147 should give us 0.6393. Okay. Any questions? No, a lot of math. But nothing hard, right? Who said multiplication and addition was hard? Okay. Luckily, we have fingers to help us out with those. But yes. No questions? How would we find power? So we got a couple equations for power, IV, or if we want to get in terms of each resistor, we have I times R squared, right? Is that I squared over R. So we'll have P. It's I squared times R, right? Let's confirm that. Yes, please. Cool. Yeah. Because when making my key, I'm pretty sure I stopped earlier. Well, we could derive it. I mean, we know P equals IV, right? That's for sure. V equals IR. So no need. Thank you, Matthew, but we found it. Mm-hmm. When in doubt, start from the top and derive it. Okay. And we could have started even further back. We could have been like, power is work over time. Okay, and then from work over time, we know work is KQ times Q over R. And then if we know KQ over R is just our potential, and potential is that, times some radial distance, we'll have R squared. But let's not. Okay. That's what your book is for. So yeah, then we can have our different ones. So we'll have power equals I1 squared times R1, power equals I2 squared times R2, power equals I3 squared times R3. And that's what you do. We could plug it in, but we're like 60% into it, and we're only halfway through the review. So let's not plug in these remedial calculations, right? You guys have this from here? Everyone agree? All right. So looking at number 5. I'm just going to redraw this because it is the ink and the printer ran out while printing. But essentially, we have a really complicated circuit here with a bunch of capacitors that I made myself. Here's a capacitor, actually. Okay, it's not as pretty as I made it on Microsoft Word, but it works. Question asks, find the charge on the capacitor C2, okay, and that's just how I do subscripts on Microsoft Word. So C sub 2, if all of the capacitors have the same capacitance, which is C equals 4 microfarad, and the battery has an EMF of 7 volts. Okay, so essentially our game plan here is going to simplify it to one capacitor, right? We're going to find our equivalence capacitance. So step 1, find our equivalent capacitance, and then work out. Just kind of throw in our charges or our potential as we break it back up bigger and bigger. So essentially, then 2 will be go back with, if we know in parallel, are we going to keep V or are we going to keep our charge Q? Our potential or charge? In parallel. So we're going to keep the V. In series, we're going to keep our charge when we break it up. Okay? So how that's going to look like, we're just going to have to simplify this in many steps. So let's kind of simplify these two here, these two here, these two here, these two here. Okay, and I'm just gonna have, let's do it. Okay, and I'm gonna use numbers because if I were to use variables, again, this would be a hot mess. Okay, like if you think the last one would be a hot mess, like this one would be pretty insane. But yes, we know that we can simplify this. Okay, so this one we can't really simplify. We can simplify this into 1. This will go into 1. This will go into 1. Okay, so essentially I combined these two, these two, these two, and these two. Okay, and what would these be? Because all I did was in parallel. So we'd see that this is 4 microfarads. Our equivalent for this one would be, since they're in series, we'll use our inverse addition rule. Okay, so our C of, kind of like a second level parallel one would equal, let me not use sub 2 because that's this one right here. So C, just our new C here. So C new, whatever, will be 1 over C plus 1 over C inversed. They have the same thing, so it's going to be 2C inverse, which is equal to C over 2, right? And C was 4, thus our new one will be 2. Two microfarads, okay? And thus we'll see that here. This one will be 4. This one will be 2 that came together. This one is 1 that came together, 4. And then here we have 2. Okay? So now we can, so that came to that. This is going to simplify. Let's start with our battery. Come here. Can't simplify that. We could simplify this in parallel. Can't simplify this with anything. And then we could simplify this into 1. Okay, so here we're going to keep the 4. This one will be new, but this one's cake because we're going to simply add them together, right? So 2 plus 4 is just 6. This one stays as 2. This one stays as 2. This one, what do we do here? Okay, yeah, so I added these two together, so then we'll have 6 here as well. Awesome. So then let's simplify this again. Okay, so we'll have our final, not our final circuit, sorry to get your hopes up. We'll have to find the equivalence of these 3. Okay, so our C of 4, 6, and 2 is going to be 1 over 4 plus 1 over 6 plus 1 over 2 inversed. Okay, I'm just going to plug this into my calculator because I have one of those. So we'll have 1 divided by 4 plus 1 divided by 6 plus 1 divided by 2, close parentheses, to the power of negative 1, and then we get 1.09, and then that's repeating, right? So I'll have over here 1.09 repeating. Finish this up. We simply add these two together to give us 8. And now we're almost there. Okay, and then this one will be found by, just, C of 1.09 comma 8 will be 1 over 1.09 repeating plus 1 over 8 inversed, which gives us C, the subunit?
Yeah.
I just did 1.09 comma 8, just to name like what I'm having here, okay? So, where was I? Oh yeah, so 1 divided by 1.09090909 plus 1 divided by 8 to the inverse, and click enter. Thus we get 0.96. Okay, so here we have 0.96. Okay, so let's find what the charge would be on this capacitor. What equation do we know to find charge on a capacitor? Q equals CV, is that correct? Awesome. So we know C, which is 0.96. and this will be total, potential total. And then our potential of the battery, okay, is given by 7 volts. It's given by 7. Thus, if we calculate this out, we'll have 0.96 times 7 equals 6.72 coulombs. Okay? So now we break it up, looking back at our second one. Since we broke them up in series, we look at our kind of key here. We'll keep the charge on each. Okay? So thus, the charge on each of these will be the same as we determined here, 6.72. But if we want to break it up further, we need to find the potential. So the potential of, let's see, we don't even need to do the potential of 1.09. We just need to keep breaking up the 8, because that's where we're going to find our C2. So you could break up all this and kind of keep going and whatnot, but like this half, we don't care about. Okay, we don't care about. So we're just going to focus on breaking up this side. So actually, I kind of started writing V sub 1.09, but I don't care about that. V sub 8. So the potential at our 8 microfarad capacitor. Oh, hold on. And this isn't coulomb, this is microcoulomb, right? Because this is microfarad. Okay? Y'all gotta catch me on this. I could, yeah, my what's it called? Making my key this morning ended. Last problem. Yeah, continuing on. We have V8 is equal to Q over C. Okay, and we determined Q to be 6.72 microcoulombs, and the capacitance is 8 microfarads. Thus we get 8 point what? To the -7. Are you sure? Because these will cancel. Yeah, so e to the 1. So 6.72 divided by 8. And just like you said, we got, might be, thank you for catching me, divided by 8. Volts. Okay. So we have 0.8 volts here. We're going to break this one up, following, our chain. Okay, I always like to make just kind of like this chain here. Going back on our chain, we see we break it up in parallel, so this potential will go back to each of these. Okay? So again, we only care about C2, which is in this bottom part, so we can disregard the 2 one. We know that this 6 is going to have a potential of 0.84. Thus, the Q on 6 is going to equal C times V, which our capacitance is 6 microfarads times 0.84 volts, which is 6 times 0.84. We have 5.04 microcoulombs. Okay? So now we take this, we break it up into parallel again. Okay? We had our potential as 0.84, thus these two will have the potential of 0.84. So we don't even have to do this, thinking about it. So we look at this one, we see that each of these have the same potential as this one, okay, because we just broke it up into parallel twice. So the potential from here carried on to that one, which will carry on to this one, okay. Thus, finding the charge on 2, okay, would be, Q on 2 is equal to 2 microfarads times 0.84, which equals my answer that I found previously divided by 3. 1.68 microcoulombs, okay? So that will be for here, and then we break it up one last time, okay? Thus, our charge will be the same on each. Thus, the charge on this one will be the charge on that one, and thus our Q2 equals the charge on C sub 2, which is like what we were originally looking at. So our final answer would be 1.68 microcoulombs. You see that? So let's just kind of recap this problem, because it was long, but when we did it ended up really fast. Like the starting was kind of long, but it resulted really quickly. So we have this circuit. Our game plan was to find the C equivalent and then just kind of keep going back, breaking up whether we did it in parallel or series, and then keep our potential if it was parallel, and keep our charge if it was if it was series. Well needed. Yeah. So we had this. We combined kind of all of these that are in series to give us this one, okay? And because they were in series, we had to do our inverse rule. We simplified this further by taking these two that were in parallel. Okay, so this one and this one to get this. We simplified this to this, and we simplified this to this, just being cautious of our inverse rule, right? And then we went back. So that's where things got a little tricky. We had, we found our charge total on our equivalent capacitor to be 6.72 microcoulombs. Then we broke it up into 8 and our 1.091 since it was in. Wow, we messed up, didn't we? We broke it up as if it was in parallel, keeping the same potential. But these are in fact in series. You see that? Okay, so this is why you always recheck your work too. It looks like it's in parallel, but it's not in parallel. Okay, so when we break this up, we will actually, the charge will be brought to each of these. Okay, and then we'd have to find the potential here, because Q on 8 would be different. Okay, so let's get a new piece of paper and restart, shall we? We've got time. A little bit. I mean, we have 2 problems left. We have this one and one other problem. Okay, and I could summarize that one very quickly. Well, let's take a vote. Okay, you know, I'm not a dictator here yet. Would you guys like to redo this, having fixed our mistake, or move on to the last problem? Raise your hand for moving on to the last problem. Raise your hand, fixing our mistake. Okay. So we will move on to the last problem, but let me at least summarize what we did here. Okay? So essentially what we're going to do is keep the charge. Okay, so we found the charge on this capacitor. That charge will be the same on each of these. Thus we can find new potentials for each of these. Okay. Huh? The point that, oh yeah, I know. Sorry. So we found the charge here, okay, and we bring that charge onto each of these. Okay, so we bring those charge into each of these. So we have a charge here. We break it up into, we find the potential across this 8 microfarad capacitor, and that potential will be the same for each of these, but we only care about this one. So we found the potential to find the charge on these. Thus, we broke it up into, what's it called, further into these two. Okay, so it wouldn't make things as nice, right? Because here we had to find the potential, and we brought the potential, but since it broke up into parallel, it went nicely. Here it broke up into parallel, and then we'd have to do it for the series. So here, charge, we find potential. Potential breaks up is the same. Since this potential, we use the potential found here to find the charge on this one, and then we break it up again. But since charge stays, our final charge would be C sub 2. Okay? Any questions on that process? No? Who would be able to do that? Who would be able to do this problem if like they did it themselves? Raise your hand. Good, good. Okay, at least half of you. Maybe a little less than half. But yeah, cool. If we finish this early, we'll be able to, which that won't happen. If we finish this early, we could do it. But a non-conducting sphere has a mass of 80 grams, a radius of 20 centimeters, a flat compact coil of wire with 5 turns wrapped tightly around it, with each turn concentric with the sphere. The sphere is placed on an inclined plane that slopes downward to the left, okay, making an angle theta with the horizontal so that the coil is parallel to the inclined plane. Okay, a uniform magnetic field is going up. Let's actually just draw this sphere with the coil. Okay, and we have a uniform magnetic field vertically upwards. Exits in the region of the sphere. What is the current the coil will enable? What current in the coil will enable the sphere to rest in equilibrium on the inclined plane? Okay, so let's work with that one first, and then we'll show that the result does not depend on the value of theta. Okay, so what's going on here? How could this be at rest? Shouldn't it flow down? Okay. Well, if we see there is a current going around this ball, it will create a magnetic field opposite to that of the magnetic field in the air and hold it still, right? So we'll see that the torque caused by the magnetic field must equal the torque caused by gravity, right? For it to be in equilibrium. But the hard part is, what is the torque on, what is the torque by the magnetic field and what is the torque by gravity? Do we have an equation for torque by a magnetic field? Mu cross B, awesome. But let's break up what mu is, okay? So mu cross B, and we know mu is equal to what again? NIA, awesome, thank you. So then we have NIA cross B, okay? So these are all vectors. Why not? Must equal the torque from gravity. What's our torque from gravity? Gravity. So mgh times, well, what's torque in general? Awesome. So perpendicular force times lever arm. So let's say that force is the force of gravity times our lever arm, okay? And I just use cross products because that insinuates perpendicularness or orthogonality.
So what would be the lever arm for the sphere?
The lever arm for the sphere would be its radius, because we'll pull it down, okay? So here we want to find gravity that's perpendicular to our lever arm, okay? And actually, you know, if you think about it, gravity is kind of like already perpendicular to the lever arm because we'll have some radius going here. But the gravity that actually causes the ball to roll down is that proportion of gravity that's going this way. Okay, so we'll see our force of gravity going here, but we want the force of gravity that's going along the slope, right? Okay, so if we make a triangle here, breaking up gravity from one component going in to the plane and one component going down to the plane and disregarding the component going into the plane, we'll see that if this is theta, okay, you know, all I'm doing is just kind of utilizing our triangle here. So we have our hypotenuse, our theta here. Thus the proportion going down will be FG sine of theta. Does everyone see that? Does anyone need help understanding that at all? So if you nod it, if you understand, nod your head yes. Okay, cool. Thus, we'll have, you know, the force, the magnitude of our force, since the radius is kind of like in all directions here, you know, the radius is always perpendicular, okay? But we'll have the magnitude of the force that's going down the slope equal to Fg, which, let's, you know, break up Fg real quick. What's Fg? mgh? It's just mg, okay? So mass times gravity, okay? So gravitational potential energy is mgh, okay? So we'll see m times g, okay, that's our force, sine of theta for our proportion that's going down the hill, times our lever arm, which is simply our radius. Okay, and then we have n IA cross B, okay, so our A, you know, is kind of going out that way, right? We want the cross product, you know, we could kind of simplify it such that it's the magnitude of A times the magnitude of B times sine of theta. Okay, because we want, you know, if this, we want the angle, and theta being the angle between the two vectors. Okay, and we know this theta is equal to that theta, because if we were to have no slope here, our area vector would be in line or parallel with our magnetic field vector. But as we increase this slope, right, this angle increases proportionally. And that's why they're the same. Does everyone see that? Okay, so we have this. We just solve for I. So we have I is equal to mg sine theta times r over ni. And nia b. Okay, sorry, the I is over here. So nba, like basketball. Okay, we can just say that this is a basketball here falling down the hill. And area would just be pi r squared, right? Because I don't think we're given a, but we'd have pi r squared. So this would simplify further. Oh, and I forgot the sine of theta from here. So our sines cancel. mgr over nb pi r squared. Okay, one of those r's cancel. Thus we have I is equal to mg, number of terms, times magnetic field, times pi, times r. Okay, and we kind of hit up the second question, which says, show that the result does not depend on the value of theta because our sine of theta cancel. If we increase theta, you know, essentially what's going to happen is it'll be able to roll faster but the proportion that's perpendicular will be bigger, thus our magnetic field will be stronger. Do you see that? Yes.
So if you increase theta, let's say all the way to 180, will just be like the same constant. Like
Mm-hmm.
right?
Yep, exactly.
Why did we use, see how for torque of gravity, we use mg sine of theta? Mg sine of theta is going down, it's not like the perpendicular force.
So we're looking for not the force perpendicular to the lever arm, because the lever arm of a sphere is in practically in every direction. So we're just looking for the force that's acting on the ball going down. So we wanted to find the force that's in the same direction as the incline. And that's where we got our sine of theta from. Any other questions? Yes.
For the lever arm to be like radius r, would the sphere have to be like hollow, or could it be?
No, it could be dense. It could be a solid sphere. You know, like you could go in really deep with like moment of the inertia, moment of inertia and stuff like that. But this problem, you don't have to worry about that because of the way. Let me think real quick. Because of the fact that it's not moving initially. We'll have a moment of inertia if it were to actually, like if we wanted to find, oh, how would like the magnetic field have to be for it to stop a rolling ball? Like if it was already in motion, it has that moment of inertia, but since it's still already, then we don't have to worry about it. That moment of inertia occurs once it's rolling. That make sense? Cool. Yes?
So the lever arm for the sphere is radius because the sphere rotates around it.
Mm-hmm. Yeah. Anything else before we conclude our session? No? Well, thank you guys so much for coming. I appreciate your attendance for study union, okay? Please fill out the evaluation. If you don't have an evaluation, raise your hand. I'll bring one to you.
Are you going to post the solutions?
No, but since you come to my sessions, you could have my work.